right? So I'm going to do a few more examples on continuous functions. So just recall that we said f is continuous at a point A if the function f is defined at A and the limit of f at A is equal to f of A. So that means that the left-hand limit at A and the right-hand limit at A, they are both equal to the value of the function at A. We also looked at the intermediate value theorem, which says that if f is continuous on a closed bounded interval from A to B, and L is any number between f of A and f of B, then f of C is L for some C between A and B. Okay, that means that if f takes a value at A at a B, then any value in between is taken by the function as well. So what I want to do is go over a few more examples on this, just to practice a little bit more. So let's say I have the following example. Let's say I have a function h of x, and that function is given by sine x divided by x squared minus 1. And the question is, where is h continuous? Okay, so determine where h of x is continuous. Well, we see that the numerator, right, the numerator, here I have a fraction, and the numerator and the denominator are both continuous on what? So we know that sine function is continuous everywhere. We know that a polynomial is continuous everywhere. So both of them are continuous everywhere, right? Okay. However, h of x is continuous then. So when we have a ratio, and once we determine where both numerator and the denominator are continuous, then we have to exclude the points where the denominator vanishes, right? So then h of x is continuous on, well, what do I have to exclude? The denominator vanishes at 1 and negative 1, right? So then h of x is continuous on negative infinity to negative 1 to 1, and 1 to infinity. Okay? Next example. Is f of x equals to x squared if x is larger than 1, and negative x squared if x is less than 1? Is f continuous at x equals to 1? Is the question clear to you? Now notice that the function is a piecewise defined function. Now when x is strictly less than 1, is this function continuous for any x less than 1? At any x less than 1, is this function continuous? Well, when x is less than 1, right? When x is less than 1, the function is given by this parabola, right? So when x is strictly less than 1, the function is continuous, right? When x is strictly larger than 1, this guy, the function is given by this parabola, and that's a continuous function as well, right? However, the only problem is when x is 1, because when x is 1, the function has two different, right at 1, the formula for the function changes, right? So we don't know exactly what's happening at 1. So we can check whether the function is continuous at 1 or not. How do I check? Well, I have to check whether the limit at 1 is the same as the value of the function at 1, right? So first of all, in order to see whether the function f is continuous at 1, I have to check two things, right? One is f of 1 is defined. The other one is the limit. So we have to check what? We have to check 1, f of 1 is defined, right? Is it true? It is defined? Well, yeah, because what is f of 1? F of 1 would be given by the first formula, right? It would be 1 squared, which is 1. So f of 1 is defined. The second thing that I have to check is that the limit as x going to 1 of f of x is the same as f of 1, right? That's what I have to check. Is the limit of f at 1 the same as f of 1? Well, how do I check that? Well, where are you going to plug in? So in this case, whenever you have a piecewise defined function and the formula changes at a point, if you want to know the limit at that point, you have to look at the right-hand limit and the left-hand limit, okay? So because the formula changes at 1, we have to look at what's the left-hand limit and the right-hand limit at 1. So if I look at the limit as x going to 1 from the right of f of x, what is that limit? And what's the limit when x goes to 1 from the left of f of x? Now, can you tell me the first one? Well, when x is going to 1 from the right, it means that x is larger than 1, right? If x is larger than 1, then the value of the function is what? 1. The value of the function is x squared, right? I'm saying when x is larger than 1, right? We know that x is going to 1 from the right, so x is larger than 1. And then f of x is given by x squared, and then the limit is given by what? 1, right? 1 squared, which is 1. How about the limit here? Well, now x goes to 1 from the left. It means that x is less than 1. When x is less than 1, the formula for f is what? Negative x squared. So I get negative 1 squared, which is negative 1. Whoops, they are not the same, right? So what do I see? I see that the limit at 1 of f of x is what? Does not exist, right? Does not even exist, so it cannot equal f of 1, right? It doesn't exist. So thus f is not continuous. So thus f is discontinuous at 1. Yeah.
Why did you plug in -1?
I didn't plug in -1, I plugged in 1.
Oh, okay.
Because the function is already negative x.
You're right.
Okay, so that's, let me do another example like this. Let me know if you're done writing it down. Okay, another example. Suppose I give you the function f of x, and this might be an important problem for your next exam. X plus sine x, and this is when when x is larger than 0 or equal to 0, and then it is x squared minus x if x is less than 0. This is how the function is given. The question is, where is f continuous? Okay, where is f continuous? So first of all, once again, if I look at the function strictly to the right of 0, so when x is larger than 0, the function is given by the formula x plus sine x. And x plus sine x is a continuous function everywhere, right? So I know that when x is larger than 0, the function would be continuous. Same way, when x is less than 0, strictly less than 0, the function is given by the polynomial x squared minus x, so it's continuous there as well. The only problem would be right at 0, because right at 0 the formula changes, so we don't know what's going on there, right? Is that making sense? All right, so we have to so we know that f is continuous everywhere except at 1, except possibly at 1. So we have to determine what's going on at 1. So how do I determine what's going on? Well, again, I have to check whether the function is defined at 1 and whether the limit at 1 is equal to f of 1. Well, the first thing is is f of 1 defined? Sorry, f of 0, sorry, what am I saying? We're talking about what's happening at 0, not at 1. Okay, so f of 0, is f of 0 defined? Well, f of 0 would be given by what? The first formula, right? Which is 0 plus sine 0, which is 0, right? Now, second thing that I have to check, what's the limit? What's the limit as x goes to 0 of f of x? Well, it's a very easy thing to do. I have to check the two-sided limits. The limit as x going to 0 from the right of f of x, and the limit as x going to 0 from the left of f of x. What is this? This is the limit as x going to 0 from the right, and when x is going to 0 from the right, x is bigger than 0, which means the formula is what? X plus sine x, right? And the limit here is 0. And what's the limit going to 0 from the left? Then the function is given by x squared minus x, and then the limit is again 0, right? So then we know that these two together gives me 0 for this limit, which is the same as f of 0, right? Which is the same as f of 0, so f is continuous at 0. So f is continuous at 0. So altogether my final answer, because I was asked where f is continuous, I have to also say f is continuous where? Everywhere, right? Because we saw that it's continuous on the left of 0, right of 0. Now we say it's continuous at 0, so it's continuous everywhere. Is everybody okay with that? You guys have any questions on that example? Everybody's okay? All right. Here is another example, and this will be the last one on continuous functions. So that's, let's say I have the function f of x, and it's given by root x plus x divided by x minus 1. Again, the question is, where is this function continuous, okay? Where is this function continuous? So what would you say? Root x is continuous where? Where is root x continuous? Yeah, when x is greater than 0, right? So 0 to infinity. Now I am including 0 here, but technically speaking, at 0 we only have that the function is continuous from the right. Right? Okay, so keep that in mind. Even though I'm including 0, the meaning of continuity at 0 is different from the meaning of continuity at 1 or 2 or other numbers here. Okay. How about the ratio x over x minus 1? This is continuous where? Yeah, the numerator is continuous everywhere, the denominator is continuous everywhere, so the ratio would be continuous everywhere except where the denominator vanishes, right? So this would be continuous everywhere except at 1. So how do I write it? Negative infinity to 1 and 1 to infinity, right? Is everybody okay? So, but where is f continuous? F is continuous where? Yeah, you have to look at the intersection of the two because it's a sum. So this would be from 0 to 1 and 1 to infinity, right? Is everybody okay with that? Everyone's okay? Once again, I want to warn you that the continuity at 0 is only from the right. Okay, the continuity at 0 is only from the right. Okay. This example that I just did, this was one of the problems that I gave in one of the exams in, when I taught this course before. Okay, coming soon, right? So last two examples that I did, you should look closely and make sure you can do those problems, okay? All right, so now we move on. We move on to chapter 2. And so we are now in chapter 2. And this chapter 2 is on derivative. How many of you have seen derivatives before? Okay, many of you have seen them. So, and I'm pretty sure you are excited to use all the formulas and so on. But until I get there, just be patient. We will go to the formulas, and you'll be able to use all the formulas you want. But before, we want to see what's the definition of the derivative. The derivative of f, so f is a function here, the derivative of f at some number a is given by f prime of a is equal to the limit as x going to a of f of x minus f of a divided by x minus a. And equivalently, this limit is the same as the limit as h goes to 0 of f of a plus h minus f of a divided by h. Okay, these two limits are equivalent, they are equal. Okay, all you have to do to see that they are the same is that you have to replace x by a plus h. Okay, so if you make this substitution in the first limit, you obtain the second limit, because if you replace x by a plus h, right, then x minus a is what? X minus a would be exactly h, right? So don't I then have h is x minus a? Do I have that? And so in the denominator I get h, and then if x goes to a, then h goes to 0, right? If x goes to a, then h goes to 0. So these two limits are equivalent and equal. Okay. So the derivative of f at a is given by one of these limits. Now we say that f is differentiable at a if this limit exists. If the limit doesn't exist, then we say that f is not differentiable at a. Okay. So we say that f is differentiable. F is differentiable at a if the limit exists. Otherwise, f is not differentiable. At a. Okay. So let's look at a few examples now on finding derivatives by using this definition. Example. Let's say I have the function f of x. Yeah. Last two lines. Okay. Let's say f of x is given by the function x squared, and then I want to find f prime of, let's say, the number 2. F prime is the derivative at a. So we are saying that the derivative of f at a is denoted by f prime of a. So f prime of a means the derivative of f at a. And what's the definition of this number? f prime of a, well, that number is given by this limit. Okay. Okay, so what is f prime of t? Sorry, f prime of 2. F prime of 2 then, in this case, is the limit as x approaches 2 of f of x minus f of 2 divided by x minus 2. Right? And what is that equal to? Well, we need to compute this limit. If you know how to compute limits by now, then you know what to do here. So this would be f of x is x squared, and then what is f of 2? F of 2 is 2 squared, right? Divided by x minus 2. And now if I plug in 2, what do I get? If I plug in 2, I get 0 divided by 0, right? So if I get 0 divided by 0, what was the trick? Factor out, cancel out, right? This is the limit as x going to 2. This would be x minus 2 times x plus 2 divided by x minus 2. And this would be equal to the limit as x going to 2 of x plus 2, and that limit is equal to what? 2 plus 2, which is 4. So f prime of 2 is equal to 4. So the derivative of the function x squared at 2 is given by the number 4. Yeah. Yeah. Any questions on that example? Now what I want to do though is apply the equivalent limit definition of the derivative and see if I get the same answer. Okay. Yeah. What did I do? What? Well, a mean the definition I wrote a general a, right? In the definition I said the derivative of f at a number a is given by this for any a. So if a is 2, then the derivative at 2 is given by this. What's the derivative at 3? What's the derivative at any other number, right? So I wrote a generally, right? But we can find the derivative at any number by using that limit. Was that? Scroll down? Yeah. Okay, so what I want to do is apply. Still, I have the same function and the same point 2, but I want to compute. So redo the same problem. Okay, but now I want to apply the other form of the limit definition, which is the limit as h goes to 0. And what would I get here? It's f of a plus h, right? So a is 2. So f of 2 plus h minus f of 2 divided by h. Right? This is the second limit, second form of the limit definition of the derivative. Was that? Say it again. There is no theorem, so this is the equivalent definition, right? So remember I said in the definition that f prime of a is given by this limit of this limit. Both of them, both of these limits are the same. Okay? And I'm doing that problem in both ways, and you can choose which form you want to use, okay? And my second goal is to show you that they are indeed the same, okay? So What is that equal to? Well, this is the limit as h goes to 0. What is f of 2 plus h? Well, it will be 2 plus h, what? Squared, minus 2 squared divided by h, right? Because f of x, remember, is x squared, right? F of x is x squared, so f of 2 plus h would be 2 plus h squared. Now this is equal to the limit as h goes to 0. 2 plus h squared, if I expand it, what do I get? 4 plus 4h plus h squared, and then I have a minus 4 here, divided by h. You okay with that? 2 plus h squared minus 2 squared. And 4 cancels out here, right? So what do I have? 4 cancels out, and after that 4h plus h squared, I can factor out an h and write it as 4 plus h. And now I can cancel out h. Once I cancel out h, I can plug in 0 for h and get what? The limit is 4 again. Okay, so both of these forms can be used to find the limit. You can choose which one you would want to use. Okay. In the next exam, the very first question might be that find the derivative of f at blah by using the definition of the derivative, not by formulas, by direct definition. Okay, is this clear? What's the definition of a derivative at a point? Okay. Maybe I should do another example. Suppose that I have the function f of x, which is given by x squared minus 8x plus 9. And let's say I would want to find f prime evaluated, well, let's just take, I don't know, let's take 3. Well, not 3, let's take negative 2. Well, we know that this function is a polynomial, so it's defined everywhere, so I can take the derivative at negative 2. What's the derivative at negative 2? Well, which limit definition would you want to use? Was that?
Second one.
Okay, someone has a preference for the second one, so let's use the second one. So the limit as h goes to 0, okay, it'll be f of negative 2 plus h minus f of negative 2 divided by h. Well, this is equal to the limit as h goes to 0. What is f of negative 2 plus h? Well, in the definition for f of x, you replace x by negative 2 plus h, right? So it'll be negative 2 plus h squared minus 8 times negative 2 plus h plus 9, right? So everything in the bracket is f of negative 2 plus h. What is f of negative 2? F of negative 2 would be negative 2 squared plus, minus 8 times negative 2 plus 9. So that's what I have in the brackets, and then I have over h. Everybody's okay? You plugged in negative 2, yes. Last step? Well, I am evaluating what is f of negative 2 plus h. F of negative 2 plus h, you replace x by negative 2 plus h. Here and here. So that's what you get here. By plugging in negative 2 plus h. What is f of negative 2? Well, you plug in negative 2 here, negative 2 here. That's what you get, right? Okay, so now we have to multiply out and simplify here. So this would be the limit as h goes to 0. What do I get from negative 2 plus h squared? You have to multiply negative 2 plus h, negative 2 plus h, right, by using FOIL. And then what do you get? You get 4 minus 4h plus h squared. Here you get negative 8, negative 2, that will be plus 16 minus 8h plus 9, and then minus, so this is what I have from the first brackets, and from the second brackets I get what? Negative 2 squared, right? So that's 4, and so I have a 4 plus 16, right? Plus a 9. Is that okay? Is that okay? Alright, so now notice, let's see what we have. Note that I have a 4, 16 and 9, right? I also have a 4, 16 and 9 in the first parenthesis, right? In the first pair of parentheses I have 4, 16, 9. Second pair of parentheses I also have 4, 16, 9, and they will cancel out, right? You guys agree with that? They will cancel out? Okay. Let me write one more line. What is 16 plus 9? 25 plus 4, that's 29, right? So I get 29 minus 4h plus h squared minus 29, right? From the second pair of parentheses. And then I have over h. 29 and 29 cancels out. Are we okay with that? Now, yeah, so now I get limit as h goes to 0, h times negative 4 plus h. Oh yes, I forgot to add the 4h and 8h, right? So what is that? So this would be a 12 here, right? This would be a 12 here, and h now cancels out. We are left with what? If h is 0, then I get negative 12, right? So in this case, we found that the derivative of the function at negative 2 is negative 12. Is everybody okay with that? Questions at all? Yeah, the difficulty here is the algebra, right? You have to expand negative 2 plus h squared, and then you have to multiply out, simplify out things. This is like going back to the intermediate algebra, right? Okay. They say they collect like terms and so on, right? Okay. And I will do one more like this. and hopefully that will be enough for you to go over the homework problems. So let's say I have the function h of x given by the function root x minus 2. And I need to find the derivative of this function. Can I find the derivative of this function at 0? The function is not defined at 0. You cannot find the derivative at 0. You can find the derivative at, let's say at 4, okay? 4 is in the domain of this function. Notice that what I would be getting is, by the way, the derivative of this function at 0, does it exist? The derivative of this function at 0. No, not 0, at 2. Sorry, at 2. Remember, the derivative is defined by saying that x goes to a, right? So x goes to a from both sides, okay? In this case, you can't allow x to go to 2 from the left, okay? So you can define something like f is differentiable at 2 from the right, okay? But we're not going to do that. All right, so here's the limit. As this time I'm not going to use the second one. Let's use the first one. So let's say x going to 4 then of h of x minus h of 4, right? Divided by what? X minus 4, right? The limit as x goes to 4 of h of x minus h of 4 over x minus 4. And then we plug in the values of the function in the numerator. H of x is the root of x minus 2. What is h of 4? What's that? Root of 2 divided by x minus 4. Okay, so how do I compute this limit? Substitution. Yeah, multiply. So in order to compute this limit, I have to multiply by the conjugate. So that is, I have to rationalize the numerator. So plus root 2 over root of x minus 2 plus root of 2. And so this is equal to the limit as x going to 4. Okay, notice that if I multiply out the numerators, what am I going to get? I am going to get the square of root of x minus 2, right? Root of x minus 2. I am going to get the square of that, and I am going to get the square of root of 2. And in the denominator, I am not going to multiply out. I'm going to keep it as x minus 4 times root of x minus 2 plus root of 2. Okay? The numerator becomes what? No, it is x minus 2 from the first one, and then from the second one I get negative 2, right? So I would be getting as x minus 4. So I would be getting the limit as x going to 4 of x minus 4, x minus 4, root of x minus 2 plus root 2. Notice that I can cancel out the x minus 4's, and now if I plug in 2, what do I get? Sorry, if I plug in 4, what do I get? 1 over 4 minus 2 here, right? Plus root 2. What is that? 1 over root 2 plus root 2, which is 1 over 2 root 2. So that's the derivative of the function at 4. Okay, I think that's enough practice in the class. You can try out the homework problems and see if you can do them. Is everybody doing okay? Everybody doing okay? Yeah. Okay, let me know when you're done. Now, what's the meaning of the derivative? Well, before I go there, first of all, usually, so I wrote the definition of f prime at a. The second limit was what? The limit as h goes to 0 of f of a plus h minus f of a divided by h. So here I'm saying the derivative of the function f at a particular number a. Okay. Now we also write f prime of x as the limit as h goes to 0 of f of x plus h minus f of x divided by h. Okay? Instead of a, I'm saying f prime of x. Now, what's the difference between the two? Well, they're the same thing, except that I'm saying what's the derivative at x instead of saying what's the derivative at a. However, there is a difference between the viewpoint, which is the second one, I think of that as a function. So for every value of x, I have the value of the derivative at x. Okay? So I'm not talking about the derivative at just one particular point. I'm talking about the derivative as a function. So given a function f, it has a derivative function. So I'm thinking of the second one as for every value of x, there is a value of the derivative at x. So that defines a function. Okay? And so it's called I call it the derivative function of f. And just to give you an example of that, if I have the function f of x given by let's say root x, okay, root x, then what is f prime of x? F prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And so this is equal to the limit as h goes to 0. What is f of x plus h? It will be x plus h root minus root of x divided by h. Are we okay with that? And again, how do I find this limit? I have to multiply and divide by the conjugate. And I'm not going to show you all these steps here. All I'm going to say is that if you multiply out the numerators, you're going to get the square of root of x plus h, which is x plus h, and minus the square of root of x, which would be x plus h minus x, which is the same as what? H. In the denominator, I would be getting this, and then I can cancel out the h's, and when I plug in h to be 0, oops. When I plug in h to be 0, I get 1 over root of x plus 0 plus root of x, right? And that is what? 1 over 2 root x. Okay. So what we have found is that the derivative function, so what we have found is that we started with the function f of x, which is root x, and we are saying that the derivative of the function at x is given by 1 over 2 root x. Okay. Again, instead of using x, we could have said, hey, what's the derivative of the function f at a, right? If I want to find the derivative of the function at a, then what would be my answer? 1 over 2 root of a, right? Okay. Any questions, anyone? Okay, now the meaning of the derivative. Notice that the way we defined the derivative of a function at a, how did we define? Well, it is defined in the following way, right? This is what is f prime of a? F prime of a, first of all, we are taking the ratio of what? F of a plus h minus f of a divided by h. And then we are taking the limit as h goes to 0, right? But what is this ratio? This ratio is basically, notice that the input here changes from a to a plus h, right? The input here changes from a to a plus h, right? So you're changing the input value from a to a plus h. So the input is changing by how much? H. And basically then I can think of this as the change in the value of f, right? Change in f of x divided by change in x, right? X goes from a to a plus h, right? X changes from a to a plus h, right? So the change in x is h, and the change in the value of f is f of a plus h minus f of a, right? Am I making sense? So, and then we are taking the limit as h goes to 0. So what is this giving us then? So then f prime of a, I can say this is the rate of change. The rate of change of f with respect to change of x. What kind of rate is that? It's the instantaneous rate, right? It is the instantaneous rate of change of f with respect to change of x. Is that making sense? Because you're dividing the change of f by the change of x, right? So you get the rate of change of f with respect to change of x. In other words, think about this. If f of x is giving you the distance function for a moving object, then the derivative will give you what? It'll give you the instantaneous rate of change of distance, right? Which would be the speed function. If you have f of x is giving you the position function of an object moving all along a straight line, right? Then the derivative of that position function will give you the velocity of that object. Am I making sense? Because it's the instantaneous rate of change of position. Am I making sense? So another application of the derivative is what? Think about the following. Suppose that this is my x-axis and I have my y-axis, and let's say I have the function f whose graph looks like the following. Okay, and let's say I have this point here is A. So this is the graph of f of x, and the question is, let's say, what is the slope of the tangent line at A? What's the slope of the tangent line at A? Okay. So this is the tangent line at A. So how would I find the slope of the tangent line at A? Well, let's say A plus h is this number, okay? Let's say A plus h is this number. Then the corresponding point on my graph is pretty bad to get that A plus. I'm sorry. Let me pick, this is a little bit closer here. Let's pick this point here. A plus h here. And then what is f of a, if I look at the line segment between these 2 points, okay, what's the slope of this line? What is the slope of that line? What's the height of the graph at A plus h? F of A plus h is the height of the graph at A plus h, right? And then what's the height of the graph at A? F of A. So that's the rise, and then what is the difference between the x coordinates? H, right? And so if you take the limit as h goes to 0, then if you take the limit as h goes to 0, you get the slope of the tangent. Am I making sense? So, but what is that? This is exactly the derivative of f at A, right? So the derivative of the function f at A also gives you the slope of the tangent line at A, right? The slope of the tangent line at A is given by, so this point here is the point A comma f of A, right? And we are saying that the slope of the tangent line at A is given by f prime of A. Is that making sense? Are we doing okay with that? Now, what's the equation of the tangent line at A then? What's the equation of the tangent line? Anybody? What's the equation of the tangent? Equation of the tangent line t then is what? Well, but I can use the point slope formula, right? So it is y minus f of a, right, equals to the slope is f prime of a multiplied by x minus a, right? That's the equation of the tangent at a. Are we doing okay with that? All right, so let's do an example. Remember that we looked at the function f of x equals to x squared, right? We looked at that function and we said that f prime of 2, we computed f prime of 2 to be what? 4. So we know that the graph of x squared is a parabola, and on that parabola, right, you have the point 2 and 4, right? So the graph of this is a parabola, and let's say this point here is the point 2 and 4, okay? And so that point is because if x is 2, then f of 2 is what? F of 2 is 4 as well, right? That point is 2, 4. And the derivative at 2 is also 4, right? The derivative at 2 is 4 as well. Isn't that the case, or am I making a mistake? Yeah, that was 4, right? Okay. So that's the derivative of, well, yes, it is 4. Okay. So now, what's the equation of the tangent at this point then? The equation of the tangent line at the point 2, 4 to the graph of the parabola is given by what? Well, it is y minus 4, right, equals to the slope, right? What is the slope here? 4 times x minus 2, right? Am I making sense? Okay, so generally speaking, right, what's the derivative at 2? Well, it will be y minus f of 2. Y minus f of 2 is equal to f prime of 2 times x minus 2, right? The slope of the tangent at this line. That's a bad drawing, but let me try to do it myself. The slope of the tangent at the point 2 for the function f is y minus f of 2 is f prime of 2 times x minus 2. In our case, f is the parabola x squared, so we know that f prime of 2 is 4, and f of 2 is 4 as well. Is that okay? Is that making sense? Another example. Recall that we looked at the function f of x equals to root of x, right? And we said that the derivative of this function at x is 1 over 2 times root of x, right? Are we okay with that? So then what is f prime of 2? F prime of 2 is what? 1 over 2 times root 4, right? And what is that? 1 over 2 times 2, what is? That is 1/4, right? Now, what's the graph of this function? I mean to find, thank you, I mean to find the derivative at 4, okay? Derivative at 4 would be 1 over 2 times root of 4, which would be 1/4 now.
Oh,
Okay? Now the graph of root of x looks like what? The graph of, oops. The graph of root of x looks like this, and let's say I want to find the slope of the tangent at 4, right? So let's say 4 is right here. Okay, so what would be the tangent at this point? Now, what is the height of this point? If 4 is the first coordinate, then what's the height? The height would be 2. So that's the point where I want to find the tangent at. So the equation of the tangent at the point where x is 4 is what? Y minus f of 4, right? Is equal to the derivative of the function at 4 times x minus 4. And we know that f of 4 is 2. The derivative at 4 is 1/4, so that's the slope. And I get x minus 4. So that's the equation of the tangent at 4. Is everybody okay with that? Yeah.
If we just put it in slope-intercept form,
Oh yeah, that's fine.
is that okay?
That's fine.
Okay.
Yeah.
I just know the title.
Because the thing is, you don't know the intercept right away here, right?
Right.
So all you know is that the derivative at 4 gives you the slope, and you know the point at 4 is 4/2. Okay, so it's easier to use the point slope formula here than using the slope intercept formula, because you don't know what the intercept is, unless you can find the intercept. Okay. Is everybody okay? All right. So once again, the derivative of a function at a point tells you the instantaneous rate of change of that function at that point. Okay. Again, if the function f of x gives you the position of a moving object on a straight line at time x, then the derivative gives you the velocity of that object at time x. Okay. And then if you take the second derivative, if you take the derivative of the derivative, then what happens? If you have the suppose that f of x, right? F of x gives you f of x is the position of a moving object. Yeah, moving object. You know what? Let me just say. Let me just say of an object moving along a line at time x, well, then what would be f prime of x? The f prime of x would be then the instantaneous rate of change of f at x, right? Which would be the same as what? Velocity at time x. And then if you so that this is the velocity function. Now if you take the derivative, so when I write f double prime of x, I mean that I am taking the derivative of f prime. Okay? So what is that? Well, that's the instantaneous rate of change of velocity, right? Well, and what's the term for that? Acceleration. And that is at time x. Is everybody okay? Yeah. Which one? Oh, the derivative of a function, it gives you the instantaneous rate of change of that function. So if I write f prime of x, it gives you the value of that, gives you the instantaneous rate of change of f with respect to x at x. Okay? So if f represents the position function of a moving object along a straight line, then the derivative tells you the velocity of that function at x. Now if you take the derivative of the velocity function, then you get the acceleration at x. Because the acceleration, the definition of acceleration is the rate of change of velocity. It's the rate of change of velocity. Is that making sense? So no matter what the function f is, derivative tells you the rate of change of f. Okay, the instantaneous rate of change of f with respect to x. Is everybody okay with that? Okay, so just a remark here. A couple of notations for derivative. Suppose I write y, I denote the value of f of x by y. Then sometimes people would write y prime, and sometimes people will write y prime of x to mean f prime of x. Okay? So y prime of x, they all denote the derivative of f at x. There are other notations which would be Leibniz notation, dy dx. So when we write dy dx, that also represents the f prime of x. Okay. Sometimes people would even write df derivative of f df dx. Okay. Sometimes people would use df dx for this. Here, sometimes people would even, to emphasize that they're evaluating the derivative at x, okay, they will write this. Same thing here, sometimes people would write dy dx evaluated at x, like this. Okay, so all these are notations for the same, having the same meaning. It's the derivative of the function at x. Is everybody okay with that? Okay. Yeah, I think these are all the notations that that are used. I can't think of right now if there are any other notations. Okay. Now, sometimes sometimes when we use dy dx to mean f prime of x, right? Now let's say you want to evaluate the derivative at 2, right? So how would you write that? So sometimes people would write dy dx and then you will use brackets like this and then write x equals to 2 to mean that they are taking the derivative of f at 2. Okay? So sometimes people write that to mean that you're evaluating the derivative at 2. Is that okay? All right. Any questions so far? So all I did really is I told you what is the derivative of a function at a number. It's given by the limit as x goes to a of f of x minus f of a over x minus a, or the limit as h goes to 0, f of a plus h minus f of a over h. And then I said instead of using a, we can use x, so f prime of x is the limit of f of x plus h minus f of x divided by h, and we think of that as the derivative function. Because any value of x, you have the derivative at x. So that defines a function, okay? And then we just did a bunch of examples of computing the derivative directly by using the limit definition so far, right? Is everybody okay with that? Okay, so let's take exactly 5 minutes break. We're going to resume at 11:25, okay? And when we come back, I'm going to go over some more examples, and then I'm going to give you the derivative formulas, and then you can have fun with the formulas, okay?
All right, that's good.
Yes. If you didn't get your exam, they are here. Find your own exam. Let's resume. What I want to look at the example that there are a couple of examples that I want to go through now, and sort of to see what happens when the derivative doesn't exist at a point. Okay. So let's look at the function first of all. F of x equals to absolute value of x. And you guys remember that the graph of this function looks like a V, right? Okay, the graph of this function looks like a V. Now, what's the derivative at 0? The function is defined at 0, but what's the derivative at 0? What did you say? What's the derivative of the function at 0? Do you think it exists, or do you think it doesn't exist? Why? Well, think about this. Remember what I said. The derivative of a function tells you the slope of the tangent line to the graph of the function at the point, right? F prime of A gives you the slope of the tangent at A. Now think about all the points here, right? What's the tangent line at any of these points? It's the same as the line, right? The tangent line at any of these points is the same as the line. So what's the slope of the tangent at any of these points? 1, right? This is the line y equals to x, right? So the slope of the tangent at any of these points is 1. What's the slope of the tangent at any point here? -1, right? So you approach to 0 either side, you don't get the same slope, right? So if you look at f prime of 0, by definition, this is the limit as x goes to 0 of f of x minus f of 0 divided by x minus 0, right? By definition, That's the derivative, right? Now, what is this derivative? Now, what is this limit then? Well, the limit as x going to 0. F of x is absolute value of x. What is f of 0? F of 0 is 0, right? So I get absolute value of 0 here divided by x. So this is equal to the limit as x going to 0 of absolute x over x. So how do I compute this limit? Well, let's try to get rid of the absolute value. But in order to do that, what I have to do is look at the left-hand limit and the right-hand limit. So if I look at the limit at x goes to 0 from the right of absolute value of x over x, then I would be getting, this is a limit as x going to 0 from the right of x divided by x, which is what? What is this limit? X going to 0 from the right of 1, which is 1. And what would be the limit as x going to 0 from the left of absolute value of x over x? This is the limit as x going to 0 from the left of negative x divided by x, right? Because now x is negative. So this is equal to the limit as x going to 0 from the left of negative 1, which is negative 1. So we see that the limit as x going to, so we know that f prime of 0 is given by the limit as x going to 0 of absolute value of x over x, and we know that this limit does not exist because the left-hand limit and the right-hand limit at 0, they are different, right? So it doesn't exist. So we see that the derivative at 0 doesn't exist, and at 0, what do we have? At 0, the graph has a what? At 0, the graph has a, sometimes people say I have a corner point or a sharp point, okay? So whenever you have a graph where you have a sharp or a corner point like this, the derivative doesn't exist there, okay? That is, there is no tangent line at this point. At the point 0, I don't have a tangent line. Am I making sense? You see, when we say that we have a tangent line to the graph of a function at a point, what do we mean when we say that? Imagine that you have a, so let's say I have this graph here. When I take a point like this and I say that I have a tangent line at 1, at this point, what tangent line, what line are we talking about? Well, at that point, so centered at that point, if you pick a line segment, if you pick a portion of the graph around this point, that a tiny portion would look like a straight line. Okay, that's the tangent line that we are talking about. But if you look at this point here, no matter how tiny portion you pick around this point, you will always have 3 points which are not on a straight line, right? I mean, you cannot approximate that. No matter how small portion you pick, you cannot approximate that by a straight line. Okay? So we say that at that point, you don't have a tangent line, right? Yeah. Let me know where to stop. Okay. Okay, let's look at another example. Let's take f of x to be x to the 1/3. And again, the question is, what's the derivative of f at 0? So notice that f prime of 0 would be the limit as x goes to 0 of f of x minus f of 0 divided by x minus 0. And this limit, f of x is x to the 1/3, f of 0 is 0, so I don't have to write that down. And in the denominator, I also have x, right? So then I could say that this is equal to the limit as x going to 0 of what? 1 over x to the 2/3, right? Because you subtract the exponents in this case, right? So it will be actually 1 over actually 1 minus a 1/3, which is 2/3. And this is equal to, I'm going to rewrite this as x going to 0 of 1 over x to the 2/3. Isn't that the same as x to the 1/3 squared? You guys agree with that? X to the 1/3 whole squared, that's the same as x to the 2/3. Because in this case you multiply the exponents, right? Now what's the limit? Can someone tell me what that limit is? What is that limit? What's that? Yeah, but is it, okay, it doesn't exist. I agree with you, it doesn't exist as a number. Is it infinity or negative infinity? Can I say something like that? Can I say this limit is infinity? Well, the denominator goes to 0 and it's positive, so it's positive infinity, right? This limit is positive infinity. Okay? So the derivative doesn't exist at this point. Okay? Remember I said whenever you have a ratio, the numerator goes to non-zero number, denominator goes to 0, the limit will be infinity or negative infinity, right? And in this case it's positive infinity because the ratio is positive, right? Okay. Because of the square. The ratio is positive. Okay, so now in this case, let's see how the graph looks like. The graph of this function looks like the following. The graph looks like this. So right at the point 0, what you have is that you have a vertical tangent. Okay? So in this case, the derivative doesn't exist, okay, at 0, but you have a vertical tangent. Am I making sense? So it has a vertical tangent at this point. Vertical, this is the graph of x to the 1/3. Vertical tangent at 0. Okay. So what's going on here is that, remember again, this derivative gives you the slope, right? So what happens that if you look at the as x goes to 0 from the right, the slopes here are going to infinity. The slopes here are going to infinity. Okay, same thing happens here. As x goes to 0 from the left, the slopes are going to infinity. Okay, the limit of the slopes is infinity, yeah.
What's the difference between a positive infinity slope and a negative infinity slope?
It's going to be, in both cases, you're going to get a vertical tangent.
Okay.
So even if you get a negative infinity there, you're still going to get a vertical tangent. Okay, let me give you another example, which is, let's say I have the function f of x equals to x to the 2/3. And once again, if I look at f prime of 0, it doesn't exist, okay? And I'm not going to compute the limit for you. Or maybe I should. F prime of 0 would be, in this case, what? The limit as x going to 0 of f of x minus f of 0 over x minus 0. That's the limit as x going to 0. What is f of x? That's x to the 2/3 minus 0, so I'm not going to write that, divided by x. Now this time, this is the limit as x going to 0 of 1 over x to the 1/3, right? Now notice that in this case, first of all, the limit doesn't exist as a number, and you cannot even say that it's infinity or negative infinity, right? Because if you go to 0 from the right, you get positive infinity. If you go to 0 from the left, you get negative infinity. Am I making sense? So what's going on in this case, in the graph? In this example, the graph looks like the following. It has a corner at 0, but what you could say, so the graph looks like this, okay? So what's going on here is that the slopes here are approaching infinity, okay? On the other side, the slopes are approaching negative infinity. Am I making sense? Now, you could say that the tangent line here, if you look at the tangent lines, they are becoming vertical. As we approach 0, the tangent lines are becoming vertical. Same thing happens here. The tangent lines are becoming vertical from both sides. So this is 0 here. This is 0. Again, the derivative at 0 in this case doesn't exist. Here's a fact. If f is differentiable at A, then f is continuous at A as well. So if you know that a function is differentiable at a point, then the function must be continuous at that point. Okay? So that's what this is saying. What's the contrapositive of this? This is equivalent to saying the contrapositive of this is the following. If f is not continuous at A, then f is not differentiable at A. So it's not true, however, if I say that if f is continuous at A, then f is differentiable at A, that's false. If f is continuous at A, then f is differentiable at A is false, because we just saw the function absolute value of x, right? Or we saw the function x to the 1/3, x to the 2/3. In all those cases, the function was continuous at 0, right? But the derivative did not exist at 0. The function was continuous at 0, but the derivative did not exist at 0. What we can say, though, if f is not continuous at a point, then we know that the function is not differentiable at that point. Am I making sense? So if f is not continuous at a point, then I can say that the function is not differentiable at that point. Okay, but if the function is continuous at a point, then I cannot say that the function is differentiable at that point. All right, so that's so we are pretty much done with the first two sections in chapter 2. So what I want to do now is look at the formulas. Okay, so this is section 2.3, the derivative formulas. Okay. Okay, so what are the formulas? The first one is the following. Well, this would be called the power rule, okay? This would be called the power rule. And what it says is that it says the derivative with respect to x of the function x to the n. So this symbol that I'm writing here, it means that I'm taking the derivative of the function x to the n, okay? This symbol here that I wrote, it means I'm taking the derivative of the function x to the n, okay? And the formula for this is, it is n times x to the n minus 1. Here I'm assuming that n is a positive integer, okay? N is a positive integer. Okay? Now I'm not going to give you a general proof of this, but I am going to show you some examples to see why this is true. Let's think about the function f of x equals to x, right? In this case, n is 1, right? In this case, n is 1. And so then what's the derivative? What's the derivative of f at x? Well, it is by definition the limit as h goes to 0 of f of x plus h minus f of x divided by h, and this is equal to the limit as h goes to 0 of what? X plus h minus x, right? Are we okay with that? And then isn't that the same as, well, this is the same as the limit as h goes to 0 of h divided by h, which is 1, right? So in this case, the derivative is 1, right? Which agrees with my formula here, right? If n is 1, then the derivative of actually 1 is 1 times actually 1 minus 1. Actually 1 minus 1 is actually 0, which is actually 0 is 1, right? So it agrees with my formula in this case. Let's check one more whether my formula is correct. Let's take the function f of x equals to x squared, and in this case, what's f prime of x? It is the limit. Yeah, my formula says it should be 2x, right? So let's check whether that's correct. H goes to 0 of f of x plus h minus f of x divided by h. So this is equal to the limit as h goes to 0. Here I'm just trying to show you that my formula is correct, okay? So in this case, what do I get? X plus h squared minus x squared, right? Divided by h. And if I expand the square, what do I get? I get x squared plus 2xh plus h squared minus x squared over h. X squared cancels out. So I get the limit as h goes to 0. If I factor out h, I get 2x plus h divided by h. H cancels out. Now if I plug in h to be 0, I get 2x. So I do see that my the derivative for x squared does agree with the one that I get from the formula, right? Am I making sense? If I could compute f prime f prime of x for x cubed, actually 4, actually 5, they will all agree with the formula that I gave you. Okay, and I can also give you a general proof of for any n that my formula is correct. I can directly compute f prime of x for actually n, but I don't want to spend time on that. Okay. So from now on, you can use the power rule for the derivative. The only time you're going to apply the direct definition is if I say find the derivative of this function by using the direct definition. Okay. Otherwise, you're going to use the formulas to find the derivatives. Now, the power rule that I gave you, it works more generally, okay? Theorem. This is the general power rule. And the general power rule is that for any real number r not equal to -1, the derivative with respect to x of x to the r is r times x to the r minus 1. This is the general power rule. It works with, so what this is saying that in the first power rule I said the exponent was a positive integer, right? The exponent was a positive integer. Now I'm saying the exponent could be anything at all except for -1. Okay? And the power rule still applies. What happens when... oh, I'm sorry. What am I saying? What am I saying? I am so sorry. So let me erase this. I don't really need this. Yeah. So this is the derivative of x to the r is r times x to the r minus 1, and this is going to work for any exponent. Okay. Okay. Is it well, I guess this would be very, very clear to you. I cannot give you a general proof of this at this point. How about you take the derivative of a constant function? The derivative of a constant function is simply 0. Yeah, I mean, which also makes sense. If you look at a constant function, the graph is a horizontal line, right? What's the slope at any given point? 0. So that the derivative should be 0 at any given point. Okay. Now some algebraic properties. If I have the derivative with respect to x of a constant times f of x. Now I'm not writing down all the things here, but here c is a constant. Okay, so if you have a constant multiple of a function, you can factor out the constant like this. Okay, so that's one. And then what I have is what's called the sum formula for derivatives. You take the derivative with respect to x of f of x plus g of x. So when you have a sum of functions, right? If you have a function which is a sum of other functions, then you can take the derivative term by term. Okay, so this is the same as the derivative with respect to x of f of x plus the derivative with respect to x of g of x. Am I making sense? What if you have a minus here? Then you're going to get a minus here. So with the plus, it's called the sum formula for derivative. With the minus, it's called the difference formula. Okay. So let's see how we can use those. So far, I only have a formula to find derivative of a power of x, right? So let's say I have the function f of x, which is x to the 4 minus x plus 5. Okay? So then what's the derivative? What's the derivative? Well, by the sum and difference formulas. Oh, let me use a 3 here, okay? By the sum and difference formulas, I can say that this is the derivative with respect to x of 3x to the 4. That is, I can take the derivative one term at a time, right? So this is the derivative of the first minus the derivative of the second term plus the derivative of the third term. And I could do that because of the second formula, the second part of the previous theorem. And then the first part of the previous theorem says if I have a constant factor, that can be taken outside of the derivative. So this is the 3 times the derivative with respect to x of x to the 4 minus the derivative with respect to x of x plus, well, the derivative of a constant function is 0. So the derivative of 5 would be 0. And we can apply the power rule for the derivative of x to the 4. So what is that? 4 times x to the 4 minus 1 minus, this would be 1 times x to the 1 minus 1, right? So this would be 3 times 4 would be what? 12x cubed and minus 1, right? Is everybody okay? Now, you don't have to show all these steps. I'm just showing you how we are using the theorem to find this derivative. But usually I would rather have you go from here all the way up here. Okay? Just find the derivative in one line. Okay? Okay, so everybody sees how these theorems apply. Okay. So now this is a very important formula. This is for the derivative of the product of two functions. Okay, this is called the product formula. The product formula. So what it says is that if I am taking the derivative of a product of two functions, f of x times g of x, unfortunately the derivative is not just f prime of x times g prime of x. Okay, if it were, then it would have been nicer, but the derivative is instead given by the following. The derivative of, there are two factors in it, right? F of x and g of x. You take the derivative of one factor multiplied by the other, plus you do the opposite now, you take f of x times g prime of x. Okay, so it's the derivative of the first factor multiplied by the second factor, plus the first factor multiplied by the derivative of the second factor. Am I making sense? Derivative of the first factor multiplied by the second factor, plus the first factor multiplied by the derivative of the second factor. Okay, you guys can remember this? Usual errors people make when they use this formula is instead of a plus, sometimes they would write minus. And usually that's the one that I see. Usually people do remember the derivative of one factor multiplied by the other. So this is called the product formula. So here is an example of using that. Let's say I have the function. Let's say I have to find the derivative of the product, which is given by x to the 4 minus x squared plus x plus 1, and then I have another factor which is x cubed plus 5x squared plus 10. So let's say I have to find the derivative of this product, right? Now notice that one thing I could do is that I can multiply out, right? I can multiply out, and then if I multiply out, I'm going to get powers of x only, right? And then I can take the derivative one term at a time and use the power rule. However, we don't have to do that. We can apply the product formula. So by the product formula, what is that? It is, you take the derivative of the first factor. So you take the derivative of the first factor, x to the 4 minus x squared plus x plus 1. And then you multiply that by the second factor, x cubed plus 5x squared plus 10. And then plus, you do the opposite now, right? You take the first factor, x to the 4 minus x squared plus x plus 1. You multiply that by the derivative of the second factor, x cubed plus 5x squared plus 10. Everybody sees what I did? What's the derivative of the first factor then? It is by applying the power rule, right? I can find the derivative one term at a time and keep applying the power rule. So what's the derivative of x to the 4? 4x cubed, right? What's the derivative of x squared? 2x. What's the derivative of x? What's the derivative of 1? 0. So I get this. Multiplied by x cubed plus 5x squared plus 10, right? And then from the second, I have x to the 4 minus x squared plus x plus 1. And then I multiply by the derivative of x cubed plus 5x squared plus 10. What's the derivative of x cubed? What's the derivative of 5x squared? 10x, right? It will be 5 times 2x, which would be 10x. And the derivative of 10 is 0, right? So that's all I get. Is everybody okay with this? You can leave your answer right there, okay? Sometimes in the exam I see that people multiply out everything here, okay? And then I tell them when I return the exam is that if you want to multiply here, why don't you just rather multiply right here, right? Why even apply the product rule? Am I making sense? I could have multiplied here and then take the derivative. Then my answer would be simplified. So if I'm applying the product rule to escape multiplying, why would I multiply here, okay? So don't multiply out. This is you can leave your final answer right there. Now, if we need to multiply out because we have some other purpose in mind, then go ahead and do that. But unless if the only question is to find the derivative, in this case, you don't have to do anything else. Okay, this is your final answer. Is everybody okay with that? All right, so that's how we apply the product rule. Any questions on that? You guys need time to write it down? Okay. The next example, the next theorem. What was that? I don't know. I'm just writing. I didn't number them, so I don't know exactly how many theorems that we have gone through. Okay. So here's another theorem. I mean, it doesn't really matter how many theorems because I can write one theorem and write down everything, all the formulas in one theorem, right? Or I could just do it separately. Okay. So here's the quotient rule. Quotient. Quotient rule. So we have looked at the power rule. We looked at the sum and difference rule. We looked at the product rule. Now we are looking at the quotient rule. So this is the rule on finding the derivative of a quotient. So let's say I have the derivative of f of x divided by g of x. How would I find the derivative of a quotient like this? The derivative of a quotient, again, it's not simply f prime of x divided by g prime of x. What it is it looks strange. What it is, you take the derivative function, you take the denominator and then you square that. So in the denominator you have the square of the denominator. In the numerator, what happens? You have the denominator g of x multiplied by the derivative of the numerator f of x minus the numerator multiplied by the derivative of the denominator. Am I making sense? So the quotient rule is you take the square of the denominator, and in the numerator you have denominator multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator. Now, those of you who remember from high school teachers have rather nice ways of making students sing and remember formulas, right? So in high school, students would say, sing this formula as I think this way. This would be called the low. This would be called the high because it's on top, high and low, and so this would be called low D high. D means derivative, so low D high minus high D low over low low. Right? Low D high D low minus low D high minus high D low over low low, right? Because we have the square, right? Is that making sense? Low D high, D means derivative. So you take low derivative of high minus high D low, high derivative of low over low low. Okay? I'm pretty sure most of you have seen something like that in high school. If you have taken calculus in high school. Okay? All right, so that's the quotient rule, and let's see how we could apply that. Should we sing this to remember this? No. Okay. All right. All right. So here's an example. Let's say I want to take the derivative with respect to x of x plus 1 over x plus 2. So let's say I want to find the derivative of this ratio. Well, my formula says in the denominator I will have the square of the denominator, so I get x plus 2 squared. Okay. And in the numerator I'm going to have x plus 2, that's the denominator, first. Multiply that by the derivative of the numerator x plus 1. And then minus x plus 1, that's the numerator, and multiply that by the derivative of the denominator. Is that making sense? So what do I have? I have x plus 2 multiplied by what? The derivative of x plus 1 is what? Yeah, it will be derivative of x, which is 1, plus the derivative of 1, which is 0. So I get 1 plus 0 minus x plus 1 times 1 plus 0 again. The derivative of x is 1, the derivative of 2 is 0, over x plus 2 squared, which is x plus 2 minus x plus 1 over x plus 2 squared, and together what is that? 1 over x plus 2 squared. So that's the derivative in this case. Does everyone see how the quotient rule is applied? Everybody's okay with that? Okay, so I want to go over more examples now. Yeah, go up. Okay, so for the rest of the time, I'm just going to go over some examples of using all these formulas that we learned. Suppose that I have the function f of x equals to x to the 463. Okay, what's the derivative? by the power rule, this is 463 times x to the power 462, right? You decrease the exponent by 1, right? So we used the power rule there. If I have the function h of x to be, let's say, the third root of, cubic root of x to the 4, right? What's the derivative of this function? What is the derivative of this function? How would you find that? Well, the first thing you need to do is that you need to write this as x to the, can I say this is x to the 4/3? Okay, now I apply the power rule, the general power rule, right? H prime of x would be 4/3 x to the 4/3 minus 1, right? That's the general power rule. So what is that equal to? 4/3 x to the 4/3 minus 1 is what? Everybody says that. It's 1/3. 4/3 minus a 1, that's 1/3. So that's the derivative, okay? Another example. What if I have the derivative with respect to x of x to the pi? Remember, the pi is the number which is approximately 3.14, right? So this will be pi times actually pi minus 1, and there is nothing else you want to write. Okay. Let's say I have the function g of x, and the function g of x is 4 times x to the 5 plus 3x squared times the root of x minus 1 over x. Again, you want to find the derivative of the function. Okay, what is g prime of x? So we are going to, first of all, what I want to do is the second term and the third term, right? If I want, I could apply the quotient rule to find the derivative of this term. But that will be too much work to find the derivative. We can just express this as what? First of all, the middle term is what? X to the half here, right? And 1 over x, isn't that the same as x to the negative 1? Okay. This is not the derivative, I'm sorry. I'm just trying to write everything as powers of x, okay? So this will be 4 times x to the 5 plus 3 times x squared times x to the half is what? X to the 2 plus half, right? X to the 2 plus half. And what is x to the 2 plus half? X to the 5 half, right? You guys are okay? Alright, 4x to the 5. I don't have to simplify anymore. So what is g prime of x then? Well, I'm going to be applying all the rules that I have learned, right? I can take the derivative of each term separately, right? I can take the derivative one term at a time. I can apply the power rule. So here this would be what? 4 times the derivative of x to the 5, right? What's the derivative of x to the 5? 5x to the 4. Here I'm going to get 3 multiplied by the derivative of x to the 5 half. What is that? 5 half x to the 5 half minus 1, right? minus, what's the derivative of x to the negative 1? Negative 1 x to the negative 1 minus 1, right? Okay, so what is that? 20 x to the 4 plus 15 half x to the what? 3 half, and this would be a plus x to the negative 2, right? Is everybody doing okay with that? Everybody's okay? Another example. Let's say I have the function which I denote by y, x squared plus 4x plus 3 divided by root of x. How would you find the derivative of this function? I am going to find the derivative of this function in two different ways, okay? First of all, I'm going to apply the quotient rule and see what I get. So remember, when I write y, I can use y prime to denote the derivative. So y prime would be what? You're going to square the denominator, right? What do you get? Get x. In the numerator, you get the denominator multiplied by the derivative of the numerator. So what's the derivative of the numerator? What's the derivative of the numerator? 2x plus 4. Derivative of 4x is 4, right? And derivative of 3 is 0, so I'm going to be done here. And then here I get minus the numerator x squared plus 4x plus 3 multiplied by the derivative of what? Root x, right? What's the derivative of root x? Notice that root x is the same as x to the half, right? So you can find the derivative of that by using the power rule. So what is that? 1/2 x to the half minus 1, right? So, and again, x to the half minus 1, I can just write it as x to the negative half, right? Now, I'm not going to simplify it anymore here, but the point is, when you apply the quotient rule here, notice that if I have to simplify this derivative, there is a lot of work to do, right? Now, compare this, now redo the problem. And I'm going to, first of all, write y in the following way. X squared divided by root x plus 4x divided by root x plus 3 over root x, right? What is x squared over root x? Root x means actually half, right? So that means this is what? X to the 2 minus a half, right? This would be 4 times x to the 1 minus a half, right? And this would be 3 times x to the what? Can I say that? You guys agree with that? 1 over root x, right? This guy is the same as 1 over x to the half, right? And 1 over x to the half is the same as x to the negative half. Maybe I should maybe I'm going to write one more line here. 1 over x to the half is what I have. And what do I have then? I have actually 2 minus a half is what? 2 minus a half is 3 half. And plus 4 times, this is actually half, plus 3 times actually negative half. So I wrote everything in terms of powers of x. Now I write y prime would be 3 half x to the 3 half minus 1 plus 4 times half x to the half minus 1 plus 3 times a negative half x to the negative half minus 1, right? Are we okay with that? I'm using the power rule, right? So this would be 3 half x to the 3 half minus 1 is what? X to the half, right? This would be 2 x to the negative half minus 3 half x to the negative 3 half, right? Are we okay with that? Are we okay? Now notice that the second way was we got a simplified answer much easier than you can imagine. In order to simplify this first answer would be much more work. So my point is, if you can find the derivative without using the quotient rule, that's what you should do if you want to simplify the answer easier, in an easier way. Okay. And same goes to product rule. If you can find the derivative without using the product rule, you should probably do that. But sometimes you just can't avoid those two rules, right? In that case, just apply those rules. Am I making sense? Okay. All right, so I think I'm going to end here. Before you leave, though, I am going to assign the homeworks from these 3 sections. In section 2.3, I still want to do a few more examples and exercises, but you can start doing the problems. So section 2.1. Section 2.1, please look at problem 5 and 7. Okay, problem 11. Okay, problem 15. Uh, 27. 29, 31, 33 and 35. Oh, I'm sorry. Cancel out 35, write 37, okay? 33 and 37. Okay, did you guys get that? Okay, 2.2. 2.2, 1, 3, 5, 7, 9, and 11. Okay, 1, 3, 5, 7, 9, 11, right? 19 through 29 odd. 19 through 29 odd. 35 and 37 and 45. You guys got that? Okay. Okay, section 2.3. 1 to 22 odd, 25 to 44 odd. 44 odd. Okay, and number 51 and number 59. Got that? All right. Now it might seem like a lot of problems, but most of them are just finding derivatives. Some of them are recognizing the graphs and so on. So you should start on this today, and tomorrow, as I said, I'm going to go over some more examples, some more exercises, so you have enough practice for the problems. Yeah. Yeah.